In the previous lesson, you learned about writing an equilibrium constant, and we used the letter K to represent equilibrium. Today, we are going to look at a specific type of equilibrium called solubility product constant, represented by KSP. Well, the S is for solubility, the P is for product, and remember, this is a constant. That means it doesn't change. So what does it mean by that? Well, this KSP describes the dissociation of an ionic compound. So different type of ionic compound will have different constant values of KSP that tell you if they dissociate, that indicate the level of dissociation in water. If that's the case, higher KSP would have a greater dissociation. And of course, if you have low KSP, you would have a lesser amount of dissociation for that particular ionic compound. That means it doesn't dissociate a lot in water. Then we also have another term called molar solubility. And basically, different substance will have different molar solubility, which indicate the number of substance that will dissolve in 1 liter of water. And one thing you need to realize that this molar solubility can be changed based on different condition of that solution. Let's try a problem together. I have magnesium hydroxide has a KSP of 8.9 times 10 to the negative 12 at room temperature. Determine the molar solubility of Mg. Determine the molar solubility of magnesium hydroxide. And if you notice how magnesium hydroxide, based on the solubility rules, this is not going to be soluble. And if you notice the values of KSP for magnesium hydroxide, it is extremely small. That means it's not going to dissolve a lot. And if you look at the KSP of magnesium hydroxide, you notice it's extremely small. That's negative 12. So it's not going to dissociate in water a lot. The first thing you need to realize is that this is a chemical reaction process where the ionic compound dissolves into ions. So let's write a balanced chemical equation for it. So we have a balanced chemical equation. Now we set up the ice table. And notice how magnesium hydroxide is solid, so we can ignore this whole entire thing because our equilibrium constant would not include any solid or liquid. Let's go back to the ice table. Initially, all of your substance will be reactant and you wouldn't have any product in the first place. Then we go down to C for changes. Of course, now we're going to apply the concept where on the product side, we're going to plus 1x. That's because the coefficient here is 1. Then right here, we would be plus 2x, okay? Then after that, at equilibrium, what do we have? 0 plus x, that gives us x right there. And here we have 0 plus 2x, that gives us 2x right there. So that is at equilibrium. Now let's combine with the KSP. So we know that KSP is equal to the product over the reactant as always. But we ignore the solid. So in this case, we just have the product. And when you write your KSP, be careful, that coefficient right there, it is for the exponent. You don't have to write 2OH minus because it's already here already. So let's plug this in. Now at equilibrium, what do we have for Mg? We have X. And then for the hydroxide, what do we have? It is 2X. What about for the hydroxide? It is 2X. So now we have 2x to the second power. So this 2x right here is for this part right there, okay? So be careful with that. Now let's plug this in for your KSP, which is given to us 8.9 times 10 to the negative 12, okay? So let's do the math over here first. 2x to the square, that is 4x squared, and we multiply that by x over here. What do we have? We would have 4x to the cube, okay? And then we just bring this down here, 8.9 times 10 to the negative 12. Now let's plug in and now let's solve for x using your algebra skill. In this case, I would divide both sides by 4, okay? That would cancel out. And then in order to get rid of that to the power 3, I would need to take the square root to the third of it, which in this case would look like this. Just remember to put parentheses when you do your calculation on a calculator. So negative 12 divided by 4. And then we're going to plug into a calculator. You look at your calculator, there should be something look like this. So in order to type this in, you would type this. It will look like, and this part would go right here. Now I plug in the calculator and my X values turn out to be 1.31 times 10 to the negative 4 molarity. And this is the number of moles that the substance will dissolve in 1 liter of solution, which is the same thing as the definition for molarity. Now let's do the opposite of it. Let's assume that we are going to calculate for KSP and we are given the molar solubility. And what we just saw over here is the molar solubility of magnesium hydroxide. Okay, now let's do this other way around. So the same thing, always write your reaction first. And then the same thing again, your ice table. And of course the solid, it can be ignored because we don't include any solid or liquid in our equilibrium constant. And then again, we would have 0 initially. Then the change would be plus x, and here would be plus 2x again. And at equilibrium, 0 plus x, that gives us x, and 0 plus 2x gives us 2x again. But now we know what is that x is going to be. That is your molar solubility right there. And all you have to do to calculate for KSP is just plug in the formula. Well, KSP at equilibrium, remember, is x times 2x to the square. And all you have to do is plug this in. So plug in for x. Well, in this case, x is going to be equal to what? Well, that x is equal to 1.31 times 10 to the negative 4. And right here will be 2 times 1.31 times 10 to the negative 4, which give us equal to 2.62 times 10 to the negative 4 if we plug it into a calculator. Now we know what it is going to be like. So now we just plug this in here, okay? And we plug this into formula. And all you have to do now is just type in your calculator. 1.31 to the negative 4 times 2.62 times 10 to the negative 4 to the second power. And what do we have? And it turned out that we have 8.99 times 10 to the negative 12. And that is extremely close to our KSP right here. Isn't that amazing? So that's how you apply the solubility rules to solve for the solubility product constant, or the molar solubility of a substance.